Sir, today basically the topic of our one day this 2 hours program is electronic and photonic sensors, on which you are doing a lot of work in your laboratory. I would like to introduce Dr. Meherwan, who is a scientist at Council of Scientific and Industrial Research (CSR) laboratory, one of the laboratory which is National Institute of Science, Communication and Policy Research. It is in Pusa. He did his PhD from Allahabad University and postdoctoral fellowship at IIT Kharagpur. He has been actively involved in setting up micro or nano robotics and fabrication facility at Advanced Technology Development Center, Indian Institute of Technology, Kharagpur. He had been helping in making the design of the facility from pre-installation preparations to installations of sophisticated instruments. He has expertise in electron microscopy, micro nano fabrication technologies like focused ion beam lithography, electron beam lithography, and two photon polymerization based 3D lithography, etc., including micro robotic manipulation. His interest span through materials sciences, ultrasonics, and metrology in general. He is an associate editor, science reporter, a popular science magazine, scientific editor, Indian Journal of Pure and Applied Sciences, former editor, Indian Journal of Engineering and Material Sciences. He has written or translated several popular science books. He is a member of the prestigious Indian National Young Academy of Science. He is a member of executive councils of several scientific societies such as Ultrasonic Society of India, Indian Science Writers Association, etc., including life member of a number of prestigious profession bodies. Sir, I think it will be very less, as you have an experience and working of the research in your field, large number of technologies which you have developed and the large number of research papers you have published. So it is just I'm showing a deepak to the sun. So you have a lot of experience, sir. Actually, now, apart from this, we would like to take your help for some development of new technologies. If you can help us, you can do some MOU. We can sign an MOU also through your this society of ultrasonics with this legal methodology, in which we can work together, because we have already signed. We not actually signed. We are already the member of MSI, Metrology Society of India, National Physical Laboratory. We can also be the member of your society, ultrasonics, because we are working in legal methodology in flow meters also. So, sir, my request is you can think of it. And secondly, sir, we are also organizing one internship program with the electrical engineering students of MITS Gwalior. If you can support us for doing some better project work for guiding these children to develop something which will be very helpful in future for these children, it will be a great help, sir. We would like to see you in these associations, collaborations, sir. Now it over to you, sir, please.
Thank you so much, Dr. Ashutosh Agarwal, sir.
Sir, we have with us our director, Shri B.N. Dikshit Saab. I would like to request him if he can kindly speak 2 words before we start. Shri B.N. Dikshit Saab.
Ashutosh ji, good morning.
Good morning, sir.
And good morning to all the participants. Happy Lohri. And Pongal is also started. And tomorrow the Makar Sankranti is also there. So good wishes to all the people. So this is a very good seminar where the people are getting the opportunity to submit their views on the topics and allied topics what has been given by the Department of Consumer Affairs, RSL Ahmedabad, Deputy Director Sri Ashutosh Agarwal ji. So this is spreading the knowledge in different field. I hope that the people will take the advantage from this very knowledge, and I wish for the success of the study. Thank you, sir.
Thank you very much, sir. Thank you very much for your kind words, sir. Now, I would like to request Dr. Mehrwan Saab to kindly enlighten us about his knowledge, about his lot of hard work, research work which he has done in his life. Thank you, sir. Please, sir.
Thank you so much, sir. I am deeply indebted to your kind words and the uh, prologue by our Honorable Dr. B.N. Dikshit, sir. He is such a lighthouse of knowledge in the field of metrology, and I was following him for some time, and um, I have seen his lectures, and I have seen people appreciating him a lot and his about his knowledge. So thank you so much, sir, for being here. And I thank, first of all, Dr. Ashutosh Agarwal, Deputy Director Legal Metrology, for his kind invitation for sharing my work here in this prestigious platform. I thank your whole team for inviting me. So let me share my presentation. So as you all know that the topic of my presentation is electronic and photonic sensors. So I will cover a few type of photonic sensors and few types of electronic sensors in this topic. The topic is pretty technical, so I will try my best to keep it simple for the common audience. And if you feel that things are a bit complex, please ask me to make it simple for you, and I would be greatly happy to convey my topics. So let us talk about chemical sensors in general. So what is a chemical sensor? So chemical sensor is a sensitive equipment which actually sense the stimuli produced by the chemical compounds in general. So if you want to sense a chemical or anything, a sensor is something, a very sensitive device which senses the change in atmosphere ambience, and it gives you a signal which you can measure. So the chemical sensors are the sensors which basically sense uh, chemicals, different form of chemicals, such as they might be gases, they might be liquid. So and generally the chemical sensors are of many types. So let us talk about the types of chemical sensors which are very common. So there are calorimetric sensors in which the heat is involved, so we measure heat. Many times there are electrochemical sensors where we measure voltage, current, or conductivity of the our sensing component. There are biological sensors. So in biological sensors, a lot of chemistry is involved, and then the electronics are also involved. So generally, these sensors are many times based on measuring the current or voltage or conductivity when we talk about the electronic sensors. So we actually couple electronics and chemistry, or sometimes a bit of biology, to sense different kind of chemicals. So what is important? So for a chemical sensor, selectivity is very important. So if we want to sense something, the sensor should only sense that compound only. So there are I mean many kind of work which are done on the on improving the selectivity of the sensors. So whenever we talk about the sensors, the first questions comes that what is the selectivity of sensor? So this is the diagram which actually shows that, I mean, how the things are sensed. So we have different kind of chemical products like gases or aromatic compounds or VOCs or liquids even. So there is a sensitive component of which is the actual sensor, and when these gases or liquid actually comes into contact with the sensing element, the gases actually get absorbed on the surface of sensor, and that absorption gives you a signal in form of either resistance or current or voltage, whatever you say, whatever you measure. So then the electronics is involved, and I will show you the sensor actually later. So we measure current. So the current measuring capability or the resistance measuring capability should be very precise, very accurate if you want to measure very small amount of currents. And then we have the analytical results, and you can see that these are the here we can analyze the results. So let us talk about the chemical sensors, especially the sensors which we have worked in our laboratory. So ammonia is a very common compound in our air, and we generally comes into contact with ammonia, and it's a hazardous gas. So we try to sense the ammonia with the different kind of materials. So let me talk to you about these materials. So generally, the sensors which actually available are the metal organic sensors. So the metal organic sensors are very robust sensors, very nice sensors, and they work very efficiently, which are available in the market. But the problem with these kind of sensors is these sensors work at very high temperatures, sometimes at 200 degrees centigrade also. So if you want to work with these kind of sensors, you need to have a heater also, micro heater many times. If your sensing area is very small, then you need to integrate a micro heater. And if you want to integrate another kind of device in your device, the process becomes lengthy, and the cost is also involved in that, and the process also become a bit complex. So to avoid this heating kind of extra step, people thought, can we sense the elements at the or compounds at the room temperature? So people try to examine the materials which are not metal oxides in general. So they try to explore the sulfides and other kind of materials, and also the polymers. So uh, WS2 is a very special kind of material, which is metal dichalcogenide, and these kind of metals are actually rocking in the field of science nowadays. You must have been heard that graphene especially was given the Nobel Prize. So the two-dimensional metal dichalcogenides are the compounds which are in news, because when we talk about the 2D materials, and especially the graphene which got the Nobel Prize in 2009, uh, the problem with graphene is graphene does not have the band gap, and because it does not have a band gap, it cannot be used as semiconductor, and because it cannot be used as semiconductor, so you cannot make a diode or transistors with the help of graphene. And these kind of devices help you making very advanced kind of electronics. So people try to create the band gap in graphene artificially, but I mean, they were successful also, but the process was very complex and cannot be transformed into industry. So people thought, I mean, can we have the materials which are having the band gap and band gap which is required for the devices, and can we make two-dimensional materials of those materials which can be utilized and which can be used as graphene, and can we make advanced electronics with those materials? So people have explored two-dimensional molybdenum sulfide and tungsten sulfide, especially these kind of materials. So tungsten sulfide is also a very good material, but I will show you that it does not sense ammonia per se. So people thought that, I mean, uh, let us make composites of things. So composites are the materials when, I mean, they are not just the mixtures. So when we have two materials and two materials are not having the competent kind of qualities for doing a task, if we combine those materials, so in such a way that the performance become many times greater, then we call it the composites. So for this, uh, we tried to combine with this PANI, which is the short form acronym of polyaniline, and we tried to make nanofibers because if we talk about nanotechnology, the best part of nanotechnology is that if you want to do something, you have very high surface area. You can think of a very big ball, like few centimeters diameter. If you calculate the area, the total surface area of the ball, it will be very small in comparison to the balls. If we make very small kind of balls of the same volume, so the many small ball will have very large surface area. So, and a very high surface area is always required for sensing kind of applications. So this is called the surface to volume ratio in terms of nanotechnology. So surface to volume ratio is very high when we go smaller. So if you go micro to nano, the surface to volume ratio is of the ratio of 1,000. So the surface to volume ratio is 1,000 times greater than in nano regime in comparison to micro regime. So always the nanoparticles are good to have if we want to do some applications like sensing. So what we did, we prepared the nanoflakes of two-dimensional nanoflakes of the tungsten disulfide, which is the metal dicarbonate counterpart of graphene. And then also we make polyaniline nanofibers, and we make a composite of these materials by chemical methods. So if we talk about how we prepared these kind of two-dimensional materials of tungsten disulfide, these were prepared by the lithium intercalation method. And so lithium intercalation method is nothing but we know that we have the layered materials like tungsten disulfide, and we want to peel off the layers one by one. So in the lithium intercalation method, we have lithium and it goes inside the layers, and then we somehow uh, 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 peels the layers with the help of lithium. So chemically we synthesize tungsten disulfide, and chemically also we synthesize polynanofiber. And in the process of making polynanofibers, we embedded these tungsten disulfide nanoflakes in the fibers. You can see here, and we, with the help of different characterization techniques, we confirm the synthesis of polynanofibers and the tungsten disulfide. Also, you can see the Raman peaks here, which are corresponding to tungsten disulfide, and this is the multi-layered tungsten disulfide. It is confirmed by the transmission electron microscopy also that this is multi-layered, and then there are other functional groups we can see from the FTIR and UV. So this is the basically setup by which the sensing is done. So these are the interdigitated electrodes. So interdigitated electrodes are nothing but there are electrodes which are set up like this, and these are the bigger pads where we put the larger electrodes for measuring the current or voltage, and the material is actually deposited on this. So the nanomaterial was deposited on this, and the electrode were put here, and we measured the electrical properties, I should say resistance especially, of the device. And this is dry air, this is aqueous ammonia, and this bubbler, this is test chamber. So the ammonia goes from here, and these are the mass flow controllers. So mass flow controllers basically controls the flow of the gas. We know that how much gas is going into the test chamber, and then we have semiconductor parameter analyzer, which basically measures the which accurately measures the electrical properties, and then we have data acquisition system, obviously. So at different concentrations, we measured the gas, and it is at the room temperature, especially. If you see here, interesting thing is polyaniline is not a very good sensor for ammonia. Tungsten sulfide is not at all a sensor for ammonia. But if we make a composite of it, it is sensing nicely. So at 10% around, we optimize the process that the sensing is the highest. And we have checked it with different ppms also. So we increase the ppm level in the steps and see that our sensor could sense the gas. And this is also a temperature profile of the sensor. So if we increase the temperature, the response is decreasing uh, with the temperature. So it's working best at the room temperature. And this is the time. So with time, how it is, degrading, and it is not degrading that greatly. So in around 1 month, around 3% of response was a decrease. So this is not very appreciable. But yeah, it is very selective. It is very selective. You can see that it's sensing ammonia very nicely. So this is kind of a sensor we make in our laboratory, different kind of sensors for different kind of gases. So carbon nanotubes are also the very interesting kind of materials. So we make carbon nanotubes in the lab. So we have an indigenous facility. We have fabricated this in our lab to synthesize carbon nanotubes with chemical vapor deposition method, and this is for silicon carbide. So different materials were basically tested for different kind of sensing applications of different gases. But the interesting part which I want to show here is the sensing of hydrogen, because uh, we know that the a large amount of nanomaterial, how it behaves, but we generally do not know the behavior of a single nanotube or single nanowire, that how it behaves exactly. So, and what are the it is required to actually understand the mechanism very minutely. So what I tried to do, I thought that let us make a single nanowire device. So with the single nanowire, we will be able to check that how the morphology of the nanowire actually plays the role in sensing, and how the sensing behavior changes with the um, morphology of the and dimensions of the platinum nanowire. So this is an scanning electron microscopy image. This area is around 50 microns, and this is nanowire. This is platinum nanowire. Platinum is known for sensing hydrogen, and it's a very nice sensor, very established kind of sensor for sensing hydrogen. And this is AFM image. AFM also shows that the diameter of this nanowire is around 400 nanometers, and the length is around 60 kind of microns of this nanowire. It's hard to actually have a single nanowire on two electrodes, and it took around a few months to make it. But yeah, we wanted to understand the behavior of the single nanowire. There are not many groups in India who are actually working directly with single nanowires even now. So when we tried to purge the gas in the chamber, and when we tried to measure the change in resistance because of the gas, we could find that the change in signal is much less than the noise which we were getting. So the system was not that much sensitive, the electronic system. And the second, the problem was the uh, the surface area which is available for adsorption of hydrogen gas was not enough to give you a clear signal, I mean clear change in the signal. So what I tried that on a interdigitated electrode, I tried to put several platinum nanowires. You can see here very, if you see carefully, there are many nanowires exactly put in the line on the interdigitated electrode. So it was a very tough task actually to pick a single nanowire and put somewhere, because you can sense that the nano scale is 1,000 times smaller than the micro scale. And if you talk about the micro scale also, if you talk about the thickness of human hair, it's around generally 200 to 300 microns. So if you can sense the miniaturization, you will understand that uh, the thickness of a micron would be around 200 times smaller than the thickness of our human hair, and again 1,000 times smaller than it would be reaching in the nanoscale. So since this is 400 nanometers, I mean, still there is a lot of miniaturization in the process, but still we are not getting very good signals because of the very less surface area. So the work is in process. And we also tried for carbon nanotubes and how carbon nanotube behave. A single carbon nanotube behaves with in terms of gas absorption and the process of sensing. So we are trying to understand such kind of behaviors. We actually these are the pictures, SEM pictures. You can see the scale also here. This is around 10 microns. So these are the zinc oxide nanowires. So we thought let us try the conventional kind of metal oxide nanowires. So zinc oxide nanowires is this, and these are the platinum electrodes again deposited by the gas injection system with the help of focused ion beam. And so platinum is very nice material for making electrodes, and we could sense the material here. Then we again tried to see a different kind of materials with, I talked about molybdenum sulfide also. So these are the molybdenum sulfide flakes which are actually prepared by the chemical vapor deposition method. So in this method, what happens? I mean, we have sulfur powder and we have either molybdenum or metal basically deposited on semiconducting or substrate or or silica substrate, and then when we evaporate this sulfur powder and we have very high temperature of this molybdenum substrate also, it actually reacts with molybdenum and it becomes MOS2. And then there are other variations of such kind of setups also. So we again prepared a different kind of chemical vapor deposition setup, and this is two zone setup. So if you want to heat the sulfur powder, you need different temperature, and if you want to have the reaction temperature, you need different kind of reaction temperature. So you cannot have a single tube single temperature furnace, so you need to have dual zone furnace. So we fabricated, actually assembled a dual zone furnace also in the lab at IIT Kharagpur. And this is the single nanoflake. You can see here it's around 4 micron, the face is around 4 micron. And these are the platinum electrodes. And with the help of these very miniaturized electrodes, we could uh, measure the resistance of this flake. But again, the that's if we talk about the sensing of different gases, the absorption was too small, so we were not able to detect the signal. So let us. So we thought, I mean, let us think about different kind of sensors. Electronic sensors are having a few limitations, although they are very good and they are in the market. But if you want to sense something which is at distance, at a very large distance, and you don't want to go there, like if you want to sense something uh, which is explosive or which is stored at a very long distance, then if you want to have electronic sensors, you need to uh, have amplification system. And for current carrying wires also, if you are having very long wires, then the signal might be needing amplification, and it's hard to have very long wires also with such kind of sensors. So I have compared it here. For electronic sensor, generally the change in signal is very small. We have discussed earlier, and the amplification of signal is needed in the circuit, so it's needed always, can't be placed at long distances, and the degradation of sensing materials also happen. I have shown you potential fire threat also due to a spark. So if you want to have if you want to sense a gas where an explosive is stored, it's risky to put the electronic sensors. They can be the source of spark also, and the cost is also good. So in the case of photonic sensing, I mean, uh, change in signal is very high uh, in many cases, and the amplification of signal is not needed in the circuit, can be placed at long distances. How can we put these sensors, especially the photonic sensor, at long distances? I will discuss. And the sensing materials are also many times very stable. These are relatively fast also. I didn't mention, I mean, in a very elaborate way, in the case of electronic sensor, I mean, absorption of the material takes some time. And when we purge the gas in to the chamber, it takes some time to have the signal. Let me show you. If you see here, the signal is not just directly high. So there is some, we need some time here. And if the gas is stopped also, I mean, this also takes some time. So changes are not directly uh, very sharp. So in the case of photonics, these kind of transitions are very sharp. And for photonic sensors, especially, the fire threat is not there. So if you're handling with the light, it will not create fire as it is possible in the case of electronics. So there are different kind of photonic sensors, but we tried to have the uh, waveguide sensors in our first experiment. So generally, if we talk about the electronics, we were measuring resistance or voltage or current or conductivity of the materials. But in the case of photonics, I mean, it's very conventional to measure the refractive index of the surroundings. So the change of refractive index is measured, and this is measured very minutely, so that if a very small change can also be detected. And you must have read during your studies, during 12th or maybe in BSc, if somebody has done BSc with physics, that the Michelson interferometer, the interferometer especially, are very sensitive for the changes, and they can be used very efficiently as the sensors. So this Mach Zehnder kind of interferometer is also very similar to the Michelson interferometer in the design. So we have a laser and we have a waveguide. So it has two components basically. So it actually divides and goes here and goes here. And if this is not the same as to this arm, there is a phase difference. And due to the phase difference created, you get the interference pattern. And that can be measured in the reverse manner also, that how much phase difference, how much the length difference is here. So very small change you can have the you can see in the pattern. And we tried with measuring the refractive index here, so we could see that at different concentrations we have peak shift in the results. But and yeah, this concentration is because of the we used sodium chloride solution. So sodium chloride solution is a very conventional kind of solution for getting very precise refractive index. So different concentrations, it has different refractive index, and the range is good. Uh, so we can see that the peak shift is happening here. But these kind of sensors cannot be integrated. I mean, it cannot be integrated easily on the integrated circuits. So we thought, I mean, let us try something which is much more I mean, which can have many more applications. And especially we were trying to have some application which is related to the long distance. So if we talk about the long distance, optical fibers are very conventional. We know now that uh, we are talking by sitting in our homes or in offices at this moment with this team WebEx, is because of the data transmission through optical fibers. And now data transmission from optical fibers become much more conventional. So optical fibers are very efficient tools to transport the signals basically. And the best part in the optical fibers is that the transmission loss is very small, because it actually works on the principle of total internal reflection. So the loss is very small, especially the transmission loss in the signals. So what can be done? So it's very conventional that the signals are being transported from one place to other place, like for few kilometers or several thousands of kilometers, uh, with the help of optical fibers. So it was imagined that if we can integrate a component or sensing component on the tip of optical fiber. So again, let me tell you why to integrate on the tip of optical fiber. Because if you want to couple two devices, or to I mean, couple the light from this optical fiber to a device, there is a coupling loss always. And sometimes to minimize the coupling loss is very challenging. So to avoid this problem also, we thought that let us try to integrate a device on the tip of optical fiber. And it's not the first time. There are many people who have done this earlier, and there are many conventional kind of devices coupled on the tip of optical fiber. This is also yeah. Let me tell you that the size of optical fiber also. If we talk about the optical fiber, these are the long fibers basically. And for the case of single mode optical fiber, the core diameter is around 8 microns. So if you compare with the thickness of our hair, it's around 200 to 250 micron. And if you think about the single mode optical fiber, the core diameter is around 8 micron, and then the surroundings and the cladding, it becomes around 120 kind of micron. So it's sometimes half of the thin of the our human hair. So the optical fibers are thin, and is if you want to do something on optical fiber, it's very complex, and it's a miniaturized kind of task. So people did some work. So this is also around this is under microscope. This is around 120 kind of microns. So there are different kind of components people created. So the people created cavities and the channels, and by fusion splicing and fibroparate kind of cavities, and then they put the fluorescent material. So the field was existing. And then people again tried, let me give you some overview, that if we have the gratings on the core of optical fiber. You can see here very nicely that this is core, this is cladding, and this is the polymer coating, and this is very thin. So for single mode optical fiber is around 8 microns, and for multi mode optical fibers is around 56 microns. So what people did, they did it smartly. They used UV beam to actually create the grating kind of patterns in the core. And what they did, uh, they use this kind of patterns to sense the materials, to sense the gases, to sense the liquids, or change the refractive index, so to say. So why do we need this kind of patterns? We need this kind of patterns to have the peaks, so that this peak is very sharp. We can measure the shift in the peak by having some material, sensing material here. So people use different geometries, this kind of geometries, and different dimensions, but uh, the problem is it is not too sensitive. Why not too sensitive? Because the sensing component comes on and sits on the surface of this, and light propagates here in the middle. So the interaction of light with these materials, so the surrounding material, is not that much. So we thought, I mean, let us try to increase the interaction surface area or interaction area of this device. So what we did, you can see here that this is the core of optical fiber, multi-mode optical fiber. So what we did, and these optical fibers are made of glasses. Those who are new to the field, they should know that these optical fibers are made of glasses. These are not metals. So if you bend those, it breaks easily. And glasses are always the uh, I mean electrically non-conductive, I should say. So if you want to do something with these glasses and the glass fibers, it's very challenging. So what we did, uh, we etched the fiber to the core, and when uh, we got the core, we etched the fiber core with the help of focused ion beam. So ion beam, focused ion beam, what it does, actually we have gallium ions, and we put it in a very high vacuum, and we use these gallium ions to etch the material. And this is etched up to the core, and around 10 microns we have etched it, and this is around 400 nanometers. So there is air, and then there is silica, and then the air, silica, and this is the pattern, and this is the basically um, pattern generated by this grating. And when we have something very with the refractive index change, we see this shift in peaks, and it was experimentally also verified. And then we did simulations also, and the simulation results and the experimentation results were very much in alignment. We found that the measure sensitivity is around 82 nanometers per refractive index unit. RIU is the unit of refractive index. So this sensitivity is good, uh, but the process of making these sensors was very complex, because if you know that um, uh, the glass fiber are the insulators or non-conductive. When we use scanning electron microscopy to see these fibers, it's very hard to see these fibers because electrons they get deposited on the surface of glass, and because of being non-conductive, we do not see patterns very nicely. And in the case of ions also, so ions are also similar to electrons, they are positively charged. So charged particles they get accumulated on the surface, and it's very hard to get the patterns with the help of focused ion beam on these non-conductive kind of surfaces. And these are really really very challenging, and it took around few months to optimize the process. And finally we could get it without coating any material. So what people do generally, if they want to make the surface patterns, they coat gold or they coat some conducting material on the surface, and then they make patterns to actually discharge the accumulation of charges. But in the case of photonic sensors, we cannot coat conductive material on the surfaces very often. So we wanted to make the patterns without coating the conducting material. And the process was optimized, and took me around a few months, 3 4 months to optimize the process. But we got very nice results. You can see very nice patterns on the core of optical fiber. And this is around 20 microns. So you can see that how miniaturized device this is. And we actually played in the micro and nano regime when we fabricated this. So, but we cannot stop here because 82, you can see the sensitivity of this device is around 82 nanometers per RIU, so it's not very great. So this is also the sensitivity of conventional FBG sensors, fiber grating sensors. But the good part is it is embedded in the fiber. So this is good part. So we can use it for the long distance kind of sensing. Um, but there are other sensors also which actually evolved in the meantime. So there are surface plasmon resonance based sensors, and these sensors are very good. Much better than the FBG sensors. You can see the sensitivity is around 300 nanometers per RIU. And then there are again the localized surface plasmon sensors, which are also, I mean, much better than the fiber we're getting sensors. So the sensitivity is around 500 nanometers per RIU. So sensitivity is much greater here in the case of in surface plasmon resonance based sensors. But the problem with surface plasmon resonance based sensors is, you have to have such kind of geometry of the device. So the incident light comes from one direction and goes in, another direction. So in the case of optical fibers, you know that the signal should come from here and signal should again go back to this side. So we cannot use this kind of geometry and this kind of technique for fibers especially. So if you want to integrate some sensor on the tip of fiber, the light should come in this direction and should go in the reverse in the opposite direction again without any deflection. So this was a challenge, but it is possible in the case of localized surface plasmon resonance-based sensors. So we thought, let us try localized surface plasmon-based sensors. So localized means what we need to have patterns on the surface of surface plasmon coating. So surface plasmon coating, we use generally a gold or some other material which are uh, suitable for this purpose. And then we make the very small, this is, you can see that this is around 500 nanometers. So this is around 250 nanometers kind of diameter of these trenches. So these are the nano trenches, uh, holes basically. And then the good sensitivity can be achieved. Then again, I talked about biological sensors also. So biological sensors are the basically integration of, biology, chemistry, and the electronics or photonics, what to say. So In this case also, if we have a surface coating, and then we have nanoparticles which are having the capture probes, then we can have the we can sense the biological material by species also. So what to do if you want to sense some biological sample? So there are some capture probes of that material, of that system, I should say. And if you can embed that capture probes on your nanoparticles, then what will happen if these specific kind of species, biological species, will come into contact of these capture probes? They will start sitting very selectively on the capture probes, and this will change the surface. This will change the reflective index, localized in the localized manner, and this will also change in the case of surface plasmon based sensors. This will change the surface plasmon resonance, and then you will have this shift in basically peak. So this kind of sensors can be used in biological sensing also. So what we did, this is tip of the optical fiber. This is basically the optical fiber of this is basically the tip of optical fiber. So if we think about the optical fiber, we cut it cross sectionally, and then you can see here that we made the patterns at the core. So this is basically the single mode optical fiber. The core is around 8 micron. So so covering the whole core, we made the pattern at around 20 micron by 20 micron area, and these are the just nano holes. And the material which we used is not gold here; it is basically chromium. And why we did not use gold? Because gold very loosely sticks on silicon dioxide, and we know that the optical fibers are made of silicon dioxide. So having the good addition, we use chromium basically. So we thought, I mean, why not to use only chromium and let us have the pattern? And so basically what we did, we took the optical fiber, which is very thin, which is made of glass, and we kept it in the optical this focused ion beam chamber. And on the tip of this, which is very small, which is very thin, you can see here, this is around 60 or 70 microns. This is because ash fiber. And then at the core, we very specifically made the pattern, which is actually in the nanoscale regime. And then we tried to simulate the pattern spectra, and then we measure the spectra. Both the spectra are very similar to say, and we got good sensitivity. Let me show you some other kind of photonic structures also, which can be used in sensing or other applications. And these are the DBR, called double bracket reflector kind of geometries. So basically you can see this is around 2.5 microns, 2.5 microns only. And these are different kind of materials. So this is silicon dioxide and titanium oxide. So this is multi-layered kind of structure, so one by one. And these were deposited by the dip coating method around 400 nanometers. And then there are I mean 20 silicon dioxide and 20 titanium oxide dioxide layers. And then we used focused ion beam to make these kind of patterns, and which is around, this is around 3 micron, which is very challenging kind of structures. And these can be used, these can be integrated on the tip of optical fiber also. And these also again can be used for the remote area location sensing and other applications also. So here also this is the concave kind of structure we've tried to make on the tip of optical fiber. This is again very small in area. This is multi-mode glass fiber with the help of focused ion beam. So in this case, also what focused ion beam does, it actually etches the material in a certain geometry. But it was very tough because again the fiber was made of glass, and we were using gallium ions. So I mean, using gallium ions for etching the the fiber was really very challenging. You can see here, this is the equipment which was used for this kind of experiments, and this is focused ion beam lithography equipment having gallium ion, and it also has the manipulation capability. So in this system, we can single-handedly pick a nanofiber or nanoparticle, and we can place it somewhere very in a very controlled manner. Although, I mean, I'm saying it very easily, but it's not very simple in doing, basically, because whenever we work with the semiconducting kind of nanoparticles, these we use electrons for seeing those particles, and when we see see the particles with the help of electrons, electrons also in the process get deposited on the surface of these particles, and the electrostatic forces actually creates too much problem in the process. So the process should have, should be optimized very nicely. It takes some time, but yeah, we could do that, and people are also doing, obviously. So, but the idea was we were etching something from the fiber. But the idea was, can we have very controlled structures on the tip of fiber? So you can see that there was a study published a few years back. What they did, this is the optical fiber basically, and they deposited a lens system on the tip of optical fiber. Very complex kind of process they actually followed, and it was a very challenging process. You can understand that if you want to deposit something on the tip of your hair also, it's very complex, and especially when you are using very miniatures kind of designs to deposit, and so it's very hard to actually locate the the tip of fiber and then doing things on the tip of fiber. So we also tried, this picture actually is from our lab. I also tried this, I personally tried this, and this is the wood pile structure I wanted to deposit on the tip of fiber. So here you can see that we could locate the center of fiber, and we could deposit something controllably on the tip of fiber. But this is not too much good, so some optimization was needed, and it's in the process. So this is the reference of this basically so the paper which was published in Nature by some other groups. So we wanted to actually follow this up for sensors, and the technology which was used to deposit these nano structures and the microstructures on the tip of fiber is basically two photon polymerization based 3D lithography. It is very specialized kind of lithography, because it uses IR laser in two photon fluorescence based technology. It actually uh, give you the 100 nanometer kind of resolution uh, with very few optimizations, I should say. So after some optimizations and some labor, you can make 100 nanometer kind of particles very nicely arranged. I will show you. So this is the diagram of this. So we have a fiber laser, which is femtosecond laser, and it has different glasses to scan. This is where we put the sample. So this is the eyepiece, and now the laser beam is scanned, and it writes basically the material. So you can see different kind of structures we prepared with this material. This is basically the microneedle of the mosquito. We all know that mosquito bites us, and we do not feel, because the mosquito needle is very small, and we feel etching basically because my mosquito actually releases some material after sucking the blood. So very small kind of needles are actually thought that for delivering the drugs, if we have very thin kind of needles which are actually similar to the mosquito needle, we should not have pain in delivering the drug. So what we prepared, this is the actual SEM image of a mosquito needle, and these are the needles which we prepared basically with the help of this two photon polymerization based 3D printing. And this is having very small features, you can say, and these are hollow needles. So their testing is being done. You can see here especially that you can see the scale here. This is around 200 nanometers. So around we can have very good resolution in the range of 100 to 200 nanometer regime. So and this is the wood pile structure. So wood pile, so woods are like you have seen the wood pile structures, and these are the coils basically, and then different kind of structures are seen here. And this is the very favorite image of mine which I used to show, because this work was done in IIT Kharagpur when I was a institute postdoc fellow there. You can see here, this is the actual main building of our IIT, and this is the 3D prototype of the building, which is basically in micron size. So this is around 80 micron high, and this is around 250 micron long. And you can see the windows here inside also. These are in a few micron size here. So we could make the 3D structures very controllably with this technique. And after coming to CSIR, I met Dr. Sanjay Yadav sir, uh, a superb human being, a very fine scientist in nature. And then I started thinking about the metrology and its importance, especially. And he actually guided to understand, and he gave the exposure of metrology to me, that how metrology is, I mean, why metrology is too important, and how things are related to metrology. Especially the sensors are uh, the basic kind of components of metrology, and metrology how it is nicely, very importantly embedded in the sensors. So both are very important uh, counterparts of the same technology. And then we wrote a article in Nature Physics, which was published last year. And I was fortunate to have the part of this team of this Nature paper, and where we discussed about why digitization of metrology is very important, and how digitization and the IoT sensors and other technologies will revolutionize the metrology. So this is the last slide of my presentation. I tried to make it very simple, and I also like to actually love to communicate my research and the complex ideas to the common public. So when we used to have the visitors, especially the students in our lab, they were like they were frightened with the technology many times, that it's too complex, and what is nice for us. So we prepared the 2 3 structures which are very small, which are related to their common life. And this structure also, you can see that this is the structure of the 3D prototype of Taj Mahal, and it has many shortcomings you can see here. But yeah, you can see the structure. So this is also around 80 micron high, and this is around 200 micron by 200 micron structure. But you can see the very small kind of features um, in the on the surface of this structure. So this can be considered as the smallest prototype ever fabricated model of a Taj Mahal, or similarly in the case of this IIT building, IIT Kharagpur main building, with the help of this technology. So this is basically to show that India and we are capable of making very small structures at the micro scale, and the and somehow towards the nano scale. uh, we have the capability to have the control mechanisms to make very small structures, and these technologies and then these tools can also be utilized in making devices. So this is all from my side. I also like, as I mentioned, I also like to communicate science to common public. In the process, I have interviewed several Nobel laureates, etc., for knowing their research, that how they actually got into research and how they excel, and how can we get inspired from them. And especially, I would like to mention the interview with Klaus von Klitzing, who is also a great meteorologist and won Nobel Prize for working in the field of metrology and others. So that's all. Thank you so much for this opportunity. I deeply indebted to the professors with whom I worked at IIT Kharagpur. I should thank all the professors, especially Professor Chapu Jacob, Professor C.S. Kumar there, and I work with a very nice team of students, PhD students there, who are at different places now. And I also want to thank at the last Dr. Sanjay Yadav sir for his guidance and giving the exposure in the field of meteorology. At last, thank you again, sir, Dr. Agarwal sir, for inviting me to this lecture. Thank you so much, sir.
Thank you. Thank you very much, sir, for your brief and very important lecture. Actually, this is the work which you have done since last many years, how the sensors, chemical sensors, and truly speaking, this was the first in my life I have heard about all this technology. We are always thankful to you, sir. And if the participants, any of the participant has any of the questions, we can do that. Santoshji, you are here. Somebody has asked about the declaration of MRP. The example given by the MRP is rupees 80, USP rupees 0.80 per ml or per gram. It is correct. You can mention it. It is correct. There is no problem. The question is very simple. Somebody has asked about the declaration of unit sale price. The explanation or the example given by the participant is correct. It can be declared in this way. Thank you very much. Santoshji, can we take the photographs of all the participants?
Yes, sir.
Please kindly make them the panelist so that we can immediately convert them, take the photographs and make them free. We are making all the participants the panelist so that we can take the pictures and we can place it on our Twitter as well as Instagram. My request to all the participants to kindly like and retweet your programs where the pictures or the photos are mentioned. We have made all the participants the panelists, not all, large number of participants we are making panelists. My request is all of them can open their cameras so that we can take the photos and we can place it on Twitter or Instagram portal. All of you who are using this your Instagram portal, kindly switch off your mic, please. Santoshji, can you take the photographs, please? Kindly switch on your camera so that we can take the pictures or putting it on the website. Twitter handle. Twitter handle is very simple. Legal Metrology India or LMGOI at LMGOI. You kindly like and retweet. LMGOI. Kindly switch off mic, please. Kindly switch off your mic and switch on your camera. Very good.
स्विच ऑन और कैमरा
हो गया डन
नहीं सर अभी वीडियो some participants have not opened the camera.
No problem. Whosoever are available, okay. Mathu साहब का मैसेज आया. He could not join. So should I ask him to join now? Santoshi, is it okay now?
Wait for a minute, sir.
The students who are doing the internship program with us, they will be joining again at 2 o'clock on the same link which we were using yesterday. This link was for only this program for 2 hours. The students of internship will join the same group, same Santoshi, the same group, the same link na which we were using yesterday at 2 o'clock.
Yes, sir.
Thank you. So we will again rejoin for the internship program students at 2 o'clock. For rest of the participants, including our expert today, Dr. Meherwan Saab, we would like to thank all Dikshit Saab, Madhu Saab, and all the participants, including the NIC team who is actually working for making these programs every week. Thank you very much. Thank you all. We are closing this session. We will meet with the internship students at 2 o'clock. Thank you. Thank you all.